A single particle of light will be the final witness to everything. This is not a story from fantasy, but the scientifically predicted end of our universe, a state called heat death. By the end of this journey, you will possess a complete understanding of the cosmos, from its fiery birth in the Big Bang to its final, frozen whisper. We will unravel the physics that dictates how stars vanish, how black holes evaporate, and how time itself may lose all meaning. What secrets are locked within the journey of that last photon, and what does its solitary path reveal about the nature of reality itself? How does it feel to contemplate the absolute end of everything? Our universe is currently in its vibrant, star-filled prime. We call this the Stelliferous Era, a time when galaxies glow brightly and new suns are born in great clouds of gas and dust. But this age of light is not permanent. It is simply the opening chapter of a much longer story. To comprehend the final photon, we must first trace the epic timeline that leads to its solitary journey. This cosmic countdown unfolds across trillions upon trillions of years, moving through distinct ages, each more alien and quiet than the last. The era of stars will eventually draw to a close. The last star will flicker out, its fuel exhausted. This marks the beginning of the Degenerate Era. Imagine a cosmos where no new stars are born. The galaxies, once brilliant spiral whirls, become dark museums filled with the fading embers of dead suns. These are white dwarfs, neutron stars, and brown dwarfs, all slowly cooling over almost unimaginable timescales. The universe grows dimmer and colder. Yet even this is not the end. Over durations so vast they defy human comprehension, even these stellar remnants will not last forever. Through a process called proton decay, the very building blocks of matter may slowly disintegrate, causing these cosmic corpses to evaporate into radiation. As this happens, the true titans of the late universe will take center stage: black holes. This begins the black hole era. For an incomprehensible length of time, these gravitational monsters will be the primary large-scale structures in existence. But they too are not eternal. They slowly leak their mass away through Hawking radiation, shrinking until they finally pop out of existence in a final, faint burst of energy. And then there is the dark era. What remains is a cosmos that is almost nothing, a near-perfect vacuum, colder than anything we can conceive, populated only by the faintest of particles and radiation stretched across an infinite-seeming expanse. The temperature of the entire universe approaches absolute zero. This is the stage set over an eternity for the final act. The journey to this point is not a sudden crash, but a slow, inevitable fade, a winding down of the cosmic clock. This accelerating expansion is not driven by the echoes of the Big Bang, but by a mysterious and dominant presence known as dark energy. Think of space itself as that stretching fabric of a balloon, but with a strange, repulsive property woven into its very essence. This property is not constant. As the universe grows larger and more empty, dark energy's influence grows stronger, becoming the overwhelming force that dictates the cosmos's ultimate fate. The evidence for this startling acceleration first came into sharp focus in the late 1990s. Astronomers studying distant stellar explosions, called Type 1, a supernova, made a shocking discovery. These exploding stars, used as cosmic mile markers, were fainter than expected. Their light was stretching across a universe that was not just expanding, but expanding faster and faster over time. This was like throwing a ball into the air and watching it not only fail to fall back down, but shoot away from you at an ever-increasing speed. Further confirmation came from the faint afterglow of the Big Bang itself, the cosmic microwave background. This ancient light carries an imprint of the early universe's structure, and its precise patterns tell us how much dark energy must exist to shape the cosmos we see today. Together, these observations painted an inescapable picture. Dark energy is the relentless engine that will tear apart the grand architecture of the cosmos. In the far future, its push will become so powerful that it will overcome the gravitational glue holding galaxy clusters together. Then, individual galaxies will be ripped apart. Eventually, even stars within those galaxies will be isolated. In the final stages, this force could tear apart planets, then atoms, and even the fabric of space-time itself in a theoretical event known as the Big Rip. But for the long, slow fade to heat death, dark energy's primary role is that of a cosmic isolator. It is the force that ensures every particle, every bit of energy, will ultimately be alone in an incomprehensible void, setting the absolute and unforgiving stage for the journey of the last photon. Our own Milky Way galaxy, a brilliant spiral of hundreds of billions of stars, will not meet its end in a dramatic collision. Instead, it will face a far more lonely and inexorable fate. The same force of dark energy that drives the universe's accelerating expansion will begin to pull the galaxy apart from the inside. Picture the space between stars not as a static emptiness, but as a fabric that is actively stretching. Over trillions of years, this stretching will become faster than the gravitational pull that binds stars together within their galactic home. The familiar constellations we know would slowly distort and drift apart, their connections severed forever. At the same time, the very fuel for new stars will vanish. The great clouds of gas and dust that coalesce to form new suns will be spread so thin across the growing cosmic void that they can no longer collapse. The last star will be born, and the universe will fall silent with the finality of a last breath. This process marks the epoch of cosmic isolation. Each star system, each solitary sun with its orbiting worlds, will become an island universe in its own right, separated from its neighbors by an ever-widening gulf of expanding darkness. The vibrant cosmic community of galaxies, a hallmark of our universe today, will dissolve into a sea of isolated points of light, each one drifting alone. This is the first great dissolution, the end of the stellar era's grand architecture and the beginning of the universe's long, slow descent into an unimaginable solitude. It is the necessary and chilling prelude to the deeper silences that await in the ages to come. The brilliant stellar era gives way to an age of profound and deepening darkness. We now enter the Degenerate Era, a period stretching across trillions of years where the universe is lit only by the fading embers of dead stars. The sky is no longer a tapestry of brilliant suns, but a cosmic graveyard populated by stellar corpses. The most common of these remnants are white dwarfs, the incredibly dense cores of stars like our own sun, which will glow for eons with nothing but their leftover heat, slowly cooling like dying coals in a vast, dark fireplace. Alongside them are neutron stars, city-sized objects so dense that a single teaspoon of their material would weigh billions of tons, and failed stars known as brown dwarfs that never ignited their fusion furnaces. This is a universe running on fumes, its once vibrant energy almost entirely spent. And yet, even these dense objects are not permanent. Over timescales that dwarf the current age of the cosmos, the very fabric of matter itself may begin to unravel. This is due to a theoretical process called proton decay. We have always thought of protons as stable, eternal building blocks of atoms, but some theories of particle physics suggest they too have a finite, if unimaginably long, lifespan. If this is true, then over countless trillions of years, the protons inside every white dwarf and neutron star will spontaneously disintegrate, causing these ultimate cosmic structures to simply evaporate into a faint mist of radiation. Another slow-acting process, quantum tunneling, could also contribute to this gradual dissolution. It allows particles to achieve the seemingly impossible, like passing through an energy barrier they shouldn't have the strength to cross. In this context, it could allow the tightly packed matter in a white dwarf to occasionally rearrange itself, very slowly triggering its transformation into iron over cosmic epochs. The darkness of this era is punctuated only by the rarest of events. An occasional, brilliant flash might occur from a chance particle-antiparticle annihilation, or from the final, dramatic collapse of a massive object into a black hole. These isolated sparks are the last, fleeting protests against the encroaching cold, a final preamble to the absolute dominion of the most perfect dark objects yet to come. Even the fading embers of degenerate matter cannot last forever. As the last white dwarfs and neutron stars slowly evaporate into nothingness through proton decay, the universe is left with its most perfect and enduring structures. We now enter the black hole era, a period of staggering duration where these gravitational titans become the sole rulers of an otherwise empty cosmos. No longer the destructive monsters of science fiction, they are now the universe's final, silent reservoirs of mass and energy, the last organized structures in a sea of expanding darkness. Imagine a space where galaxies are no longer collections of stars, but vast, swirling nests of these dark behemoths, each one a monument to gravity's ultimate victory. They drift through the void, their immense gravity warping the space around them, yet with nothing left to consume. Their reign is one of profound stillness and isolation. But in this seeming permanence lies their own inevitable end, a process dictated by the strange laws of quantum mechanics. This is Hawking radiation. Contrary to the old idea that nothing escapes a black hole, quantum theory shows that pairs of particles can spontaneously pop into existence at the very edge of its boundary, the event horizon. Occasionally, one particle falls in while the other escapes, stealing a tiny amount of the black hole's energy in the process. This results in a faint, almost undetectable glow, a whisper of heat from an object we think of as perfectly cold. Over timescales that make the age of stars seem like a single heartbeat, this slow leak causes a black hole to lose mass. It shrinks, and as it shrinks, the process accelerates. What begins as an imperceptible trickle becomes a final, rapid evaporation. The largest black holes will persist for googles of years, numbers so vast they are meaningless to the human mind, but their fate is sealed. Each one will ultimately vanish in a final, faint burst of particles and energy. This marks the end of the black hole era, the last chapter in the story of organized mass. When the final black hole blinks out of existence, the universe is left with nothing but a diffuse, cold sea of subatomic particles and radiation, a perfect void awaiting its final, solitary traveler. Stephen Hawking gifted us a profound paradox, a cosmic irony that sealed the ultimate fate of these gravitational giants. A black hole, an object so dense that not even light can escape, is not truly black. It glows. This faint, theoretical glow, known as Hawking radiation, arises from the bizarre and unpredictable nature of the quantum realm. At the very boundary of the black hole, its event horizon, empty space, is not truly empty. It is a seething foam of virtual particles, pairs of matter and antimatter that constantly flicker into and out of existence. Normally, these pairs annihilate each other almost instantly. But at the edge of the abyss, something different can happen. One particle of the pair falls into the black hole, while its partner escapes into the wider universe. To an outside observer, it appears as if the black hole has radiated a particle. The energy for this creation comes from the black hole's own mass, causing it to lose a tiny, almost immeasurable amount of weight with each emitted particle. This process is unimaginably slow for a large black hole. A typical stellar black hole might take a number with 67 digits worth of years to evaporate. For the supermassive black holes that anchor galaxies, the timescale is truly cosmic, lasting for a number of years with nearly 100 digits. Yet, in a universe with virtually infinite time, even this is a certainty. The evaporation is not a steady process. As a black hole shrinks, its temperature rises and the rate of radiation increases. The final moments are not a slow fade, but a sudden, violent pop. The last vestige of the black hole vanishes in a final, minuscule burst of high-energy particles and light. This final whisper from the last black hole is a cosmic event of ultimate finality. It is the moment when the last organized structure, the last object held together by gravity, ceases to exist. From this point forward, the universe is no longer a collection of things, but a near-perfect void of disconnected particles and stretched light, a silent and empty stage awaiting its one and only performer. While black holes slowly leak their mass away, an even more fundamental decay could be unfolding across the cosmos. The very atoms that once formed planets and people may not be permanent. Many of our most ambitious theories of physics suggest that the proton, the stable heart of every atomic nucleus, has a finite lifespan. This is the concept of proton decay. It proposes that after an unimaginably long period, a proton can simply fall apart, transforming into lighter particles and a burst of energy. Visualize every single solid object left over from the age of stars, every white dwarf, every cold, dark rock drifting in the void, not as a permanent monument but as a temporary structure. Over quadrillions upon quadrillions of years, these objects would slowly and silently evaporate from the inside out. The iron core of a dead star would not just cool, it would gradually cease to be, its fundamental building blocks dissolving into a faint, ethereal glow. Scientists have been searching for this event for decades, using enormous detectors buried deep underground to shield them from cosmic interference. They monitor vast volumes of water or other materials, waiting to see a single proton vanish, releasing a telltale flash of light. So far, no proton has been seen to decay, which tells us that if it happens at all, its average lifetime is staggeringly long, far exceeding the current age of the universe. But in the context of heat death, that immense timescale is just a single tick of the clock. If proton decay is real, it represents the ultimate victory of chaos over order. It is the mechanism that erases the last possible structures, converting every last bit of what we call stuff into a uniform, ultra-low-energy radiation field. This is the final simplification of the cosmos, a universe where matter itself is just a memory and only the most basic, formless energy remains. The last black hole has vanished, and the slow decay of protons has erased every star and planet. What remains is the Dark Era, the final and longest chapter in the history of the cosmos. The universe is now reduced to its most basic components, a sparse and ever-cooling soup of fundamental particles and radiation. Photons of light, neutrinos that barely interact with anything, and the occasional electron and its antimatter counterpart, the positron, are all that drift through an unimaginable void. The temperature everywhere plunges toward absolute zero, the point where all molecular motion ceases. To grasp the sheer emptiness, imagine a volume of space so vast it could have contained billions of galaxies, now holding nothing but a single, low-energy particle of light. This is not a void of active destruction, but one of passive, infinite dilution, Occasionally, an electron and a positron might meet and form a temporary atom called positronium. They orbit each other in a fragile dance for eons, but even this bond is fleeting. They will eventually collide and annihilate each other in a final, tiny flash of light, further simplifying the cosmic soup. Every form of energy is slowly and irrevocably stretched and spread apart by the relentless expansion of space. The universe is winding down to its simplest, most desolate possible state, a near-perfect equilibrium of cold and stillness. It is within this ultimate quiet, this final simplification of all existence, that the stage is at last set for the solitary journey of the last photon. The universe's long slide into darkness is not a random accident, but the inevitable result of one of physics' most fundamental laws. This is the second law of thermodynamics, and its consequences are absolute. At its heart is a concept called entropy, which we can think of as the universe's measure of messiness or disorder. In any isolated system, entropy always increases, moving from a state of order and concentration to one of disorder and even distribution. Your morning coffee does not spontaneously heat up. Instead, its warmth disperses into the cooler air of the room until both are the same temperature. The energy has spread out, the entropy has increased, and the system has reached a quiet, uniform state. Now apply that simple, everyday observation to the entire cosmos. The universe is the ultimate isolated system. There is no outside room for its heat to escape into. It began in the Big Bang with all its energy and matter in an incredibly hot, dense, and ordered state, a cosmic cup of coffee steaming with potential. Over trillions of years, that energy has been doing exactly what the coffee's heat does, just on a cosmic scale. Stars are brilliant, localized furnaces that burn their fuel, radiating heat out into the frigid void. Galaxies collide and mix, black holes evaporate, and particles decay. Every single process, every event that has ever occurred, from the nuclear fusion in a star's core to the firing of a neuron in your brain, has been powered by this relentless cosmic equalization, this great scattering of energy. This irreversible increase in entropy is what gives us the arrow of time itself. We remember the past as a state of lower entropy and move forward into a future of higher entropy. We can scramble an egg, but we cannot unscramble it. The universe is running down, and heat death is its final, frozen state of maximum entropy. This is the point where every gradient has been flattened. No place is hotter or colder than any other. Energy is still there, but it is now a uniform, ultra-thin background haze, incapable of ever doing work again. It is a cosmos where nothing happens, and nothing ever will, because everything that can happen already has. That final red dwarf is the universe's ultimate survivor. For trillions of years it has burned, a faint crimson ember in the overwhelming darkness, outliving every brighter star by an immense margin. But even its vast reservoir of hydrogen fuel is not infinite. Slowly, inexorably, the fusion reactions in its core begin to falter. The outward push of energy that has sustained it for eons weakens, and gravity, patient and relentless, finally wins its long-standing battle. The star contracts, its internal fires sputtering out. It does not explode. It simply cools, dimming from a deep red glow to a dull, invisible warmth, and then to the same temperature as the background of space itself. It has become a black dwarf, a cold, dark sphere of crystallized carbon and oxygen, a frozen monument to a once brilliant age. This quiet, almost imperceptible event is one of the most significant milestones in cosmic history. It marks the extinction of the last natural furnace. With that final flicker, the universe loses its primary source of heat and light forever. This is the true end of cosmic creativity. No new stars will ever be born to replace it. The grand engine of stellar nucleosynthesis, the process that forged every element essential for planets and life, has ground to a permanent halt. Every world that could have harbored life, every potential cradle for consciousness, is now frozen and dark. The vibrant, dynamic chapter of the universe, defined by the birth and death of stars, has reached its final, silent punctuation mark. The long stellar era, with all its drama and brilliance, is over. The fading of this last ember is a solemn eulogy for starlight itself. It is a transition that deepens the profound mystery of the eons to come, a signal that the cosmos is now entering a deeper, more permanent kind of night. This relentless expansion of space does more than just pull objects apart. It fundamentally alters the very light traveling through it. Every photon, every particle of light, is caught in a cosmic tug of war it cannot win. As space itself stretches, the light waves traveling across it are stretched along with it. This phenomenon is called cosmological redshift. Think of a photon as a wave on an infinitely long rubber sheet. If you suddenly stretch that sheet, the wave crests become farther apart, its wavelength growing longer. A longer wavelength means lower energy. So, as the universe expands, every single photon is systematically losing energy, becoming colder and fainter with every passing eon. To witness this is to watch the slow fading of a cosmic photograph. Consider a single photon of visible blue light, emitted from a galaxy that died eons ago. Over billions of years, that blue photon stretches, its wavelength increasing until it shifts to red light. Billions of years later, it has shifted further into the invisible infrared. Later still, it becomes a microwave photon, and eventually, it will degrade into a low-energy radio wave. Its signal so faint and spread out it is practically indistinguishable from the background silence. This process is happening to all light, everywhere. Even the most important ancient light in the universe, the cosmic microwave background radiation, is not immune. This afterglow of the Big Bang currently glows as a faint microwave signal, a remnant of a time when the universe was a hot, dense plasma. But as the eons roll on, this fossil light will continue to redshift. Its wavelength will be stretched so far that it will pass through the radio band and beyond, its energy diluted into a near-perfect uniformity with the cold vacuum of space. The history of the cosmos, written in light across the heavens, is being systematically erased, photon by photon, in a grand, slow-motion fade to black. This relentless dilution is a key mechanism of the heat death, ensuring that not only does the universe grow cold, but it also grows dark, its stories lost to an endless, expanding silence. Yet even in this absolute cold and darkness, the universe is not truly empty. The void itself is alive with a faint, ghostly energy. According to quantum field theory, what we call empty space is not a featureless nothing. It is a dynamic stage, a seething foam of virtual particles. These are not particles in the ordinary sense, but fleeting fluctuations in the underlying quantum fields that make up reality. Pairs of particles and their antimatter counterparts spontaneously blink into existence, borrowing energy from the vacuum for an impossibly short moment before colliding and vanishing back into nothingness. This continuous, frantic dance is happening everywhere, all the time, even in the deepest, darkest void between galaxies. We can even observe the effects of this quantum activity in laboratories today through a phenomenon called the Casimir effect. If you place two perfectly smooth, uncharged metal plates extremely close together in a vacuum, they will be gently pushed toward each other. Why? Because the narrow gap between the plates restricts the kinds of virtual particles that can appear there, while outside the plates, the full frenzy of the quantum foam continues unabated. The greater pressure from outside forces the plates together, a tiny but measurable force born from the energy of nothingness itself. This vacuum energy is the most fundamental background hum of reality, a baseline of activity that will persist long after the last black hole has evaporated and the last proton has decayed. It is the universe's final, irreducible state, when every star is a distant memory and every particle is isolated by cosmic distances. This quantum shimmer will remain as the sole activity in an otherwise silent cosmos. It is the permanent canvas of existence, and upon this canvas, the journey of the last photon will be the final, solitary brushstroke of visible light. These timelines are so vast they shatter our everyday sense of time. To make sense of them, we need to chart this cosmic decay, graphing the universe's future from our vibrant present to the final, frozen silence. Our journey begins now in the Stelliferous Era, a time of light that will last for roughly 10 to the 14th years, or 100 trillion years. That is when the very last star, a small, frugal red dwarf, will finally burn out, plunging the cosmos into the Degenerate Era. For another staggering span, out to about 10 to the 40th years, the universe will be a graveyard of cooling stellar corpses. It is during this era that proton decay, if it occurs, will truly take hold, slowly evaporating every remaining atomic structure. Then the black hole era begins. The largest of these gravitational giants will dominate the cosmos for an almost incomprehensible duration, up to 10 to the 100 years. That number, a googol, is a 1 followed by 100 zeros, a timescale so long that the entire stellar era preceding it is a mere blink. When the last black hole vanishes via Hawking radiation, the dark era commences, a near infinite stretch of nothingness, but the timeline does not end there. On scales that defy any meaningful description, like 10 to the power of 10 to the 50 years, the universe enters the realm of quantum possibility. In this near eternity, even the seemingly impossible becomes inevitable through a process called quantum tunneling. A lone electron drifting in the void could spontaneously tunnel into a higher energy state. Isolated particles could theoretically reassemble into entirely new forms of matter, like iron stars or Boltzmann brains, conscious entities that flicker into existence from the chaos. This timeline is not a simple countdown. It is a story of exponentially decreasing activity. The brilliant, frenetic first chapters give way to eons of deepening quiet, where the intervals between any noteworthy event stretch from millions of years to trillions, and then to timescales for which we have no name. Our current epoch, this cosmic spring teeming with stars and life, is a fleeting, precious moment in a narrative overwhelmingly dominated by cold and dark. Yet the finality of heat death is not the only story science can tell. Our current understanding points toward that frozen, silent end, but the cosmos is governed by forces we are still struggling to fully comprehend. What if the dominant force in our universe, dark energy, is not constant? Some theories suggest it could intensify over time, transforming from a slow cosmic isolator into an unstoppable shredder. This is the scenario of the Big Rip. In this frightening model, dark energy evolves into something called phantom energy, a form with such strong negative pressure that its repulsive force grows without limit. The expansion of space would not just accelerate, it would become violently exponential. The first structures to go would be galaxy clusters, torn into scattered galaxies. Then individual galaxies would be ripped apart, their stars flung into the ever-widening void. As the end approaches, the expansion force would overcome the gravity holding stars together, then the electromagnetic forces binding planets and moons. In the final, terrifying moments, the fabric of spacetime itself would be stretched faster than the speed of light, severing every atomic nucleus and every fundamental particle from one another. The universe would end not with a whimper, but with a catastrophic tear in the very canvas of reality, an instant of ultimate disintegration. This is a fate far more dramatic and sudden than the slow freeze of heat death, a possibility that hinges entirely on the still unknown nature of dark energy. But what if the story is not one of endings at all, but of cycles? An alternative vision proposes a universe of eternal rebirth, known as the Big Bounce. This idea emerges from certain interpretations of quantum gravity, suggesting that when the universe reaches a state of maximum contraction or density, a quantum repulsion effect could reverse the collapse. Instead of a singular beginning in a Big Bang, our universe may have been born from the death of a previous cosmos. It expanded from a hot, dense state and may one day contract back again, not to a point of infinite density, but to a threshold that triggers a new expansion. In this cyclical model, the universe has no true beginning or end, only an endless sequence of cosmic seasons. Each cycle would erase the past entirely, with all the structures and histories of one universe being scrambled into the primordial fire of the next. There would be no memory, no continuity, just an eternal rhythm of birth, death, and rebirth. Another speculative idea even suggests our vacuum of space is not truly stable, but merely a low-energy state in a vast cosmic landscape. A quantum fluctuation could, at any moment, trigger a bubble of a new, lower-energy vacuum to form somewhere in space. This bubble would then expand at the speed of light, rewriting the laws of physics as it goes and obliterating everything in its path. While these alternatives are compelling, the evidence for the standard heat-death model remains the strongest. The observed acceleration of the universe and the measured properties of the cosmic microwave background currently fit the slow freeze more comfortably than the dramatic rip or the cyclical bounce. Yet exploring these possibilities is crucial, for it highlights the profound unknowns that still lie at the heart of cosmology. The ultimate fate of everything may not be a foregone conclusion written in the stars, but a mystery whose final answer is still waiting to be found. So what exactly is this last photon? It is not a unique particle born from the final moments of the cosmos. Instead, it is the ultimate survivor, the very last echo of all the light that ever was. Every star that blazed, every supernova that flared, every galaxy that shimmered, contributed to a vast sea of light now slowly fading away. As the universe expands relentlessly, these photons are not only stretched to lower energies, becoming colder and fainter, they are also thinned out, scattered across an ever-growing void. The concept of the last photon is one of statistical inevitability. Given a region of space vast enough and a timeline long enough, the density of photons will drop so low that only one remains in that entire volume. This final particle of light, carrying a whisper of energy from a forgotten age of brilliance, becomes the sole representative of the universe's luminous history. It is a solitary traveler on an endless journey through a cosmos that is now absolute zero in temperature and perfect in its darkness. This photon is more than just a particle. It is a symbol of the ultimate quiet, the final point in the story where everything that once shone has been reduced to a single, fading point of light. Its lonely path marks the absolute end of the universe's capacity for illumination, the last memory in a cosmos that has forgotten what it means to glow. This single photon begins its journey in perfect darkness, a lone survivor from an age of light. It might have been born in the heart of a long-dead star, a final spark from the last black hole's evaporation, or even a relic from the primordial fire of the Big Bang itself. Whatever its origin, it is now utterly alone, the final point of light in a cosmos that has forgotten what light is. Its voyage is one of absolute and unbreakable solitude. There are no stars for it to illuminate, no dust clouds to scatter it, no retinas or instruments to ever detect its passage. It will never be absorbed, never reflected, never interrupted. It travels in a perfectly straight line through an infinite-seeming void, a silent arrow shot into an endless night. As it journeys, the relentless expansion of the universe continues its work. The very space through which this photon moves is still stretching, and with every passing eon, the photon's wavelength is pulled ever longer. Its energy, already minuscule, dwindles further. A photon that began as visible light will have long since redshifted into the infrared, then into microwaves, then into low-energy radio waves, but the process does not stop. Its wavelength is stretched toward infinity, and its energy approaches absolute zero. It becomes the faintest possible whisper in a silent universe, a single note held until the end of time. This is not just a particle's journey, it is the final story. This photon is the last witness. It carries within its quantum state a memory of cosmic dawn, of galactic empires and stellar fires, all now extinguished. It is the universe's sole remaining testament to its own brilliant, tumultuous history, a history now reduced to a single, fading day to point on an eternal journey to nowhere. To follow its path is to understand the ultimate loneliness of heat-death, not as an equation, but as the poignant, never-ending voyage of the final conscious thought in a mind that has gone forever to sleep. The human mind simply cannot grasp the temporal abyss of the Dark Era. To even begin, we must abandon our familiar scales of centuries and millennia. The numbers involved are so immense they cease to be quantities and become more like philosophical concepts. Consider the current age of our universe, roughly 13.8 billion years old. This entire vast span of cosmic history, from the Big Bang to today, is like a single solitary grain of sand. Now picture every grain of sand on every beach and in every desert across the entire planet Earth. The duration of the Dark Era is that entire planet of sand, while our universe's entire past is that one tiny grain. This analogy still falls short, but it begins to hint at the staggering emptiness of time that lies ahead. Mathematics gives us names for these numbers, like the googol, which is a 1 followed by 100 zeros. The lifetime of the largest black holes is measured in googols of years, but even a googol is practically nothing compared to a googolplex, which is a 1 followed by a googol of zeros. Writing out a googolplex in standard notation is physically impossible, as there are not enough atoms in the visible universe to serve as ink. These are the scales on which the final, slow-motion processes of the Dark Era unfold. Over these near-infinite durations, the rare electron and positron drifting in the void may eventually form positronium, a fragile atom that orbits for eons before its particles meet and annihilate in a final, tiny flash. The sheer length of time makes even the most improbable events not just possible but inevitable. A lone particle, through the quantum phenomenon known as tunneling, could spontaneously find itself in a new energy state or configuration, simply because given enough time, every possible quantum event will eventually occur. This is not a universe of dramatic change, but one of unimaginable patience, where the clock ticks so slowly that the distinction between a moment and an eternity begins to blur. That final photon's endless journey unfolds against a backdrop of near-total stillness, but the universe never achieves perfect classical silence. Even in the absolute cold and emptiness of the Dark Era, the ghostly rules of quantum mechanics guarantee that something can still happen, however rarely. This is the domain of quantum tunneling, a process that allows particles to achieve the seemingly impossible. Think of an energy barrier as a tall hill. In the classical world, a ball without enough speed to roll over the top would simply bounce back. But in the quantum realm, a particle like an electron has a tiny but real chance of simply appearing on the other side of the hill, as if it had tunneled through an invisible passage. It does not physically bore a hole, rather, its wave-like nature gives it a probabilistic footprint everywhere, allowing it to occasionally bypass restrictions in a spontaneous, unpredictable leap. Now apply this to our desolate cosmos. Picture a single electron and its antimatter twin, a positron, drifting light years apart in the void. The energy barrier between them is immense, representing the colossal distance and the forces that should keep them forever separate. Yet, because of quantum tunneling, there is a vanishingly small probability that they will suddenly find themselves bound together, forming a fragile, temporary atom called positronium. For eons, these two particles would orbit one another in the darkness, a solitary, microscopic system in an otherwise eventless expanse. Their union, however, is doomed. An electron and a positron are matter and antimatter. They cannot coexist for long. Eventually, they will collide and annihilate each other in a final, tiny flash of light, a pair of new photons bursting into existence before they too begin their own journey toward infinite redshift. The probability of such an event is almost zero on any human timescale. We are talking about odds so low that the average time between occurrences in a given volume of space could be a googol years or more. But in the eternal duration of the dark era, even the most improbable events are not just possible, they are statistically inevitable. Given enough time, everything that can happen will happen. These rare quantum phenomena become the only punctuations in the cosmic sentence. They are the universe's final, sporadic flickers, the last reminders that the vacuum is not truly empty and that perfect equilibrium is a classical illusion. In a cosmos destined for heat death, quantum tunneling ensures that the story never completely ends. It just becomes a collection of whispers separated by eternities of silence. But what happens when the last photon travels through a cosmos where nothing else occurs? We have arrived at a question that challenges the very framework of our reality. In a universe that has reached maximum entropy, a state of perfect uniformity where no heat flows and no events transpire, does time itself have any meaning? Philosophers and physicists have long grappled with this profound puzzle. We typically experience time as a sequence of cause and effect, a relentless arrow moving from an ordered past to a disordered future. This arrow is powered by change, by the constant transformation of energy from a concentrated state to a spread out one. But in the final, frozen state of heat death, all such transformations are complete. There are no hotter spots to cool down, no energy gradients to drive any process, not even the rare quantum flicker to mark a before and after. In this absolute equilibrium, the arrow of time may simply vanish. It would be like a movie screen after the film has ended, displaying only a single, static frame forever. There is no past, present, or future, because there is no change to distinguish one moment from the next. This suggests that time might not be a fundamental ingredient of the cosmos, but rather an emergent property that arises from the flow of energy and the progression of events. Without events, there is no time, only an eternal, featureless now. This leads us to a startling conclusion about the last photon. Its endless journey through the void would not be a journey through time at all, but a single, frozen thread in a static tapestry. It is the final, perfect snapshot of a story that has not only ended, but has forgotten that it ever began. So, could a future intelligence in that eternal dark ever piece together our story? The evidence would be almost non-existent. The grand, fiery birth of the Big Bang would be a forgotten myth. Its primary piece of evidence, the cosmic microwave background, would have long since been stretched into a formless, ultra-low-energy haze, its distinctive patterns smoothed into perfect uniformity. The brilliant pinwheels of galaxies, the epic explosions of supernova, the very existence of planets and life, all would leave no direct trace in that cold, sparse void. The universe would present itself as a featureless, static expanse, offering no obvious clues that it was ever anything else. This is the ultimate cosmic crime scene, where nearly every piece of evidence has been systematically destroyed by time and expansion. An archaeologist in this era would find no pottery shards, no buried cities, no fossilized bones. The only artifacts left to dig with would be the laws of physics themselves. The very constants of nature, the specific mass of an electron, the strength of the gravitational force, the precise ratio of particles to photons in the void, these fundamental numbers would be the last surviving hieroglyphs. They are the frozen data, the cosmic settings that were locked in during the universe's first moments. An advanced observer might be able to measure these constants with incredible precision. From the exact properties of the few remaining particles, they might infer that a great transformative event must have occurred, one that forged these specific values. The sheer existence of matter over antimatter, for instance, would be a monumental clue, a silent testament to a slight asymmetry in the earliest laws, a bias that allowed something to come from nothing. The large-scale geometry of the universe, whether it is perfectly flat or gently curved, would be another permanent fossil. This geometry is a direct relic of the Big Bang's explosive energy and the density of the early cosmos. By mapping the infinite void, a theorist could potentially work backwards, deducing that such a geometry could only have arisen from a hot, dense beginning. Yet these clues would be maddeningly abstract. They could point to a beginning, but they could never convey the richness of the story, the drama of stellar life and death, the emergence of consciousness, or the beautiful, intricate structures that once filled the cosmos. The history of the universe would be reduced to a set of equations, a beautiful but silent mathematical tombstone. This thought experiment reveals a profound truth about our own place in cosmic time. We are living in a uniquely privileged era, a golden window where the universe is both old enough to be comprehensible and young enough to still be filled with the evidence of its own creation. We can see the afterglow of the Big Bang. We can watch galaxies evolve. We are surrounded by the vibrant artifacts of a dynamic cosmos. This window will not last forever. In the far future, that evidence will fade, and the grand narrative of our universe will slip into an unreadable silence, leaving only the final, fundamental numbers as a whisper of all that was lost. Our ability to witness the cosmos is a gift with an expiration date. This profound idea is framed by the Anthropic Principle, a logical statement that the universe we observe must be compatible with the existence of observers. We are not passive inhabitants of a random epoch. Instead, our very presence here and now reveals something fundamental about the cosmos. We find ourselves in the Stelliferous Era, this brief window of light and structure, precisely because it is the only conceivable time that could have given rise to us. The timing is exquisitely, almost unnervingly precise. If intelligent life had emerged just a few billion years earlier, the universe would have been a far more hostile place. The first stars were massive and short-lived, exploding in violent supernova that sterilized vast regions of space. More crucially, the cosmos was still cooking its first heavy elements. There would have been no carbon for organic molecules, no oxygen for water, no iron for planetary cores. The very building blocks of life and worlds were still scattered in the ashes of those first stellar generations. Conversely, if our arrival were scheduled for the distant Degenerate Era, the situation would be equally bleak. The last stars would be flickering out, their energy fading. Without the steady, sustained warmth of a star like our Sun, complex life, as we know it, becomes impossible. The universe would be a cold, dark, and resource-depleted graveyard, offering no energy for metabolism, no light for photosynthesis, and no new elements to build with. We exist in this narrow golden zone, a sliver of cosmic time nestled between the primordial chaos and the eternal freeze. This principle transforms our perspective on the heat death. The eventual silence is not a tragedy we are doomed to witness, but the very reason we are here to contemplate it at all. Our fleeting moment of consciousness, our ability to look up at the stars and trace their epic story from birth to end, is a rare and precious privilege. It is the universe becoming aware of itself, if only for a blink of its immense eye before returning to the quiet from which it came. The profound emptiness of the dark era makes even the impossible feel inevitable. Given a near infinite amount of time, the laws of probability and quantum mechanics perform a strange magic, transforming events of unimaginable rarity into near certainties. This line of reasoning gives rise to one of the most unsettling thought experiments in all of cosmology, the concept of Boltzmann brains, named for the physicist Ludwig Boltzmann, who pondered how order could arise from chaos. A Boltzmann brain is not a biological organ. It is a self-aware entity, a complete consciousness with a full set of memories and sensations that spontaneously assembles from random quantum fluctuations in the vacuum of empty space. Picture a single, disembodied brain or a sufficiently complex computer popping into existence out of nothing, complete with the false memory of a past life, of seeing stars, of feeling the sun on its face. It would believe with absolute certainty that it was a real person in a real universe, when in fact it was just a momentary, accidental glitch in the void. The paradox is staggering. In a universe that exists for a googolplex of years, the spontaneous, random fluctuation of a single, self-aware brain is statistically more likely than the gradual, natural evolution of an entire, ordered cosmos with billions of galaxies and trillions of planets. The math suggests it is easier for the vacuum to accidentally create a solitary observer with a detailed, imaginary history than to actually build the vast, coherent universe that history describes. This idea turns our own reality into a profound question. Are we the genuine products of 13.8 billion years of cosmic evolution, or are we merely Boltzmann brains, fleeting illusions that just happened to fluctuate into existence a moment ago, with our entire past, our memories of childhood, our knowledge of the stars, all nothing more than an elaborate, pre-packaged fiction? This is not a fringe theory, but a serious logical puzzle that highlights the weirdness of infinity and probability. It implies that the dark era, that final chapter of absolute cold and silence, might not be entirely unobserved. Instead, it could be sporadically punctuated by these phantom consciousnesses, each one flickering into being, experiencing a solitary, hallucinated reality for a fleeting instant before dissolving back into the equilibrium from which it came. They would be the most lonely and improbable observers in all of existence, ghosts in a machine that has otherwise wound down to absolute zero. But if the story of the cosmos is ultimately erased, what happens to the information itself? The history of every supernova, the genetic code of every life form, the very memory of existence seems destined to vanish into the cold, silent void of heat death. Yet, one of the most fundamental tenets of quantum mechanics presents a stunning contradiction. It states that information can never be truly destroyed. It can be scrambled, transformed, and rendered utterly unrecognizable, but it is never erased from the cosmic ledger. This principle collides with our understanding of black holes in a famous puzzle known as the black hole information paradox. If you throw a book into a black hole, the book is gone, shredded by immense gravity. According to Hawking radiation, the black hole will eventually evaporate, releasing only random thermal energy back into the universe. So, what happened to the specific information contained in that book, the precise arrangement of its atoms and the words printed on its pages? For decades, this paradox suggested that information was indeed being permanently lost, violating a core law of physics. The potential resolution to this puzzle is as beautiful as it is bizarre, and it hints at a profound secret about the nature of reality. It is called the Holographic Principle. This idea proposes that our universe, with its three spatial dimensions of length, width, and height, might not be the full story. All the information needed to describe everything within a volume of space, every star, every person, every event, could be entirely encoded on a two-dimensional surface that surrounds it, like a cosmic fingerprint stored on a vast spherical shell. Think of it like watching a three-dimensional movie on a flat, two-dimensional screen. The image has depth and perspective, but all the data to create that illusion is stored on the flat surface of the screen itself. In this view, a black hole's event horizon could act as that two-dimensional screen, faithfully preserving the information of everything that falls in. The information is not destroyed. It is translated, imprinted onto the fabric of spacetime itself in a form we cannot yet decipher. This concept scales up to the entire cosmos. The information that defines our universe, every event from the Big Bang to the formation of Earth, might be encoded on a distant, two-dimensional boundary at the edge of space and time. So, as the universe approaches its final state of heat death, what becomes of this cosmic archive? The energy fades, the light dies, and all structure dissolves. But according to this principle, the story itself, the complete data set of cosmic history, might persist. It would be frozen, a timeless and inaccessible record etched onto the fundamental canvas of reality. The universe becomes a silent library, filled with books written in a language of physics that no one is left to read. This offers a strange and haunting form of permanence, a suggestion that even in the absolute cold and dark, the echo of everything that ever was remains. The cold silence of heat death may not be a permanent tomb, but merely a long winter before a new cosmic spring. A profound alternative to this finality is the idea of a cyclical universe, a grand rhythm of death and rebirth that echoes through eternity. Two particularly compelling models give this poetic idea a mathematical backbone. The first is conformal cyclic cosmology, proposed by the renowned physicist Roger Penrose. In this vision, the far, far future of our universe, a state of infinite expansion and maximum emptiness, becomes mathematically identical to the high-energy singularity of the Big Bang. The end of one cosmic cycle, or eon, seamlessly transforms into the beginning of the next. In this model, the last remnants of our universe, including that final, redshifted photon, are not lost. As its wavelength is stretched toward infinity, its energy approaches zero, but in a beautiful twist of geometry, this state of zero energy and infinite scale is reset, becoming the hot, dense seed for a new Big Bang. The last whisper of one world becomes the first cry of another. The second model, the ekpyrotic universe, paints a different but equally stunning picture. It imagines our three-dimensional cosmos as a membrane or brain floating in a higher dimensional space. The Big Bang was not a singularity from nothing. but the result of a collision between our brain and another. In this cyclical scenario, these brains are drawn together over immense timescales by an invisible force, eventually colliding and releasing a firestorm of energy that becomes the matter and radiation for a new universe. The brains then bounce apart, expand, cool, and are drawn together once more, beginning the cycle again. The evidence for these ideas is subtle but tantalizing. Penrose and his collaborators have searched for, and claim to find, faint concentric circles in the cosmic microwave background, which they interpret as the gravitational shock waves from supermassive black hole collisions in the previous eon. While this remains a highly debated claim, it represents a genuine effort to find observational clues that our universe has a past beyond the Big Bang. These theories completely transform the narrative. The journey of the last photon is no longer a lonely voyage into an eternal night, but a cosmic baton pass, a transformation from the final particle of light in a dead universe into the first quantum seed of a new reality. This vision of endless renewal, where every ending is a beginning, resonates deeply with ancient philosophical traditions from Hinduism to Stoicism, which have long contemplated the universe as an eternal wheel of time. It suggests that our vibrant cosmos, with all its stars and life, is not a fleeting accident in an otherwise silent void, but one beautiful verse in an infinite, repeating poem. Our entire forecast for the end of time rests on a monumental extrapolation. We are taking the physical laws we have verified over a mere 13.8 billion years and projecting them across trillions of years into the future. This is a necessary exercise, but it comes with a crucial caveat. Our map of reality is still incomplete, with vast territories marked only as unknown. The true nature of dark energy remains one of the greatest mysteries in science. Is it truly a constant force, as Einstein once proposed, or is it something dynamic that could change or even reverse its effect over time? Our models for the quantum vacuum are based on the physics we understand today, but a unified theory of quantum gravity, one that seamlessly merges the very large with the very small, continues to elude us. Without it, our picture of the ultimate fate of black holes and the fabric of spacetime itself is provisional. These are not small gaps, they are chasms in our understanding, and what lies within them could completely rewrite the final chapter. What if dark energy is not a cosmological constant but a field that can decay? Such an event could release a new burst of energy, potentially reigniting a cycle of cosmic formation in the distant, dark future. Or consider the unsettling possibility of vacuum decay. Our current vacuum state might not be the lowest possible energy state, but merely a stable local valley in a vast cosmic landscape. A random quantum fluctuation could, at any moment, create a bubble of a truer, lower energy vacuum. This bubble would then expand at the speed of light, its wall rewriting the fundamental laws of physics as it moves, annihilating the universe as we know it and replacing it with something entirely new and unpredictable. These are not just wild speculations, they are serious considerations born from the edges of our knowledge. Acknowledging these limits is not an admission of failure. It is the very essence of the scientific journey. It is a reminder that our story of the cosmos, from its fiery birth to its frozen end, is still a draft. The final page may contain revelations far stranger than our current physics allows us to dream. This cosmic forecast can feel like a cold splash of reality, leaving us questioning our place in a universe destined for oblivion. It is natural to feel a profound sense of existential dread, a crushing insignificance in the face of such vast scales of time and space. Our entire civilization, our art, our loves, and our struggles seem to vanish into nothing more than a momentary flicker against an eternity of silence. Yet this feeling, while valid, is based on a flawed perspective that equates permanence with purpose. The inevitable end does not erase the story. Consider a beautiful song. Its value is not diminished because the final note fades into quiet. In fact, its temporary nature is what gives the melody its emotional power and urgency. Our lives are that song. The knowledge that the universe and everything in it is transient does not make our experiences meaningless. It makes them infinitely more precious. We are the universe's way of understanding itself, a rare and fleeting moment of wakefulness in its long slumber. This brief window of light and consciousness is not a cruel joke, but an astonishing gift. It allows us to feel the warmth of the sun, to be moved by a piece of music, to experience the deep bond of love, and to gaze up at the stars and unravel their secrets. Our endeavors to create, to learn, and to connect with one another are not erased by the future cold. They are the very things that define this brilliant, temporary flash against the dark. They are what make our moment in the cosmic story significant. This perspective is not a cause for despair, but a profound call to cherish the fragile, beautiful now. Even our most ambitious projections of cosmic fate assume a universe without a guiding hand. What if intelligence itself could become a permanent feature of the cosmos, fighting the encroaching dark with sheer ingenuity? This is not mere science fiction, but a profound thought experiment that reframes the heat death from an inevitable end into the ultimate engineering challenge. Imagine a civilization that has survived the death of its star and now operates on timescales of billions of years. Its energy needs would be astronomical, leading to concepts that dwarf our current understanding of technology. One such idea is star lifting, a process where advanced society would use immense magnetic fields or other means to carefully siphon material from a star, regulating its fuel consumption and extending its lifespan from mere billions to trillions of years. This is not just maintenance but active stellar husbandry. Further into the future, when stars are gone, these cosmic engineers might turn to black hole farming. A supermassive black hole could be fed with carefully controlled amounts of matter, converting a significant portion of its mass into usable energy through processes like the Penrose mechanism, far more efficiently than any star. They could even harness the Hawking radiation from smaller, artificial black holes as potent power sources. The most extreme proposal involves creating an entire new universe in a laboratory. By concentrating an unimaginable amount of energy into a tiny space, a civilization might trigger a new Big Bang, perhaps even encoding the fundamental constants to ensure the new universe could support life. This would be the ultimate act of cosmic legacy, ensuring that the flame of consciousness is passed on. The energy requirements for such feats are beyond comprehension, and the technological hurdles may be insurmountable. Yet, the mere possibility transforms our perspective. It suggests that the final story of the universe may not be written solely by mindless physical laws, but could one day be authored by a persistent and brilliant intelligence determined to write its own ending. The universe's final temperature is a precise, measurable value, a number that defines the ultimate cold. It will not be an arbitrary chill, but a specific thermal flaw dictated by the relentless expansion and the strange, faint energy of the vacuum itself. This final metric is known as the de Sitter temperature, a concept that emerges from a cosmos completely dominated by dark energy, or a cosmological constant. In this future, the universe enters a state of exponential expansion known as a de Sitter space, a near-perfect void with a faint, intrinsic warmth that can never be extinguished. That warmth is almost unimaginably cold. The de Sitter temperature is calculated to be only about 10 to the power of negative 30 degrees Kelvin, a value so infinitesimally small it is virtually zero. To grasp this, consider that the coldest depths of intergalactic space today are a raging inferno by comparison. This residual heat comes from two primary sources. The first is the ever-redshifting cosmic background radiation, the last fossil glow of the Big Bang. Its photons are stretched to such incredibly long wavelengths and low energies that they contribute this minuscule, fading warmth. The second and more fundamental source is the quantum vacuum itself. Empty space is not truly empty, but seethes with quantum fluctuations, and this activity provides an irreducible baseline of energy, a whisper of heat that can never be removed. This final temperature is not just a number, it is the scientific quantification of the heat death itself, the exact value of the universe's ultimate equilibrium. It represents the point where no heat can flow because there is no place warmer or colder. Every particle, every ripple of energy will eventually come to this same frigid temperature, a state of perfect and unbreakable thermal balance. This is the number that defines the final silence, the ultimate cold that awaits every last thing. This entire cosmic epic is a story of transformation on the grandest possible scale. It began as a single point of unimaginable density and heat, a state of pure, featureless potential. From that ultimate simplicity, the universe exploded into being, forging the first particles, then atoms, then the glorious, complex structures of stars and galaxies. For a fleeting moment in this vast timeline, it gave rise to planets, to life, and to minds capable of looking back and asking where it all came from. We are part of a universe that became aware of itself, that learned to trace its own history and dared to forecast its own distant, cold demise. This act of cosmic self-awareness, happening here and now in our tiny corner of space and time, is arguably the universe's most stunning accomplishment. It is a brief, brilliant flash of understanding in the long dark. To reflect on this grand narrative is not to deliver a eulogy of sorrow, but one of profound awe. We are witnesses to a majestic and beautiful tragedy, a story of